Now, being able to design your own custom distributions is great. If you have a particular shape in mind, basically weights you want to assign to all of the possible outcomes, being able to very quickly turn that into a valid probability model is a fantastic skill to have. But sometimes it turns out to be reinventing the wheel because there's a small set of probability distributions that just crop up time and time again in business analytics, in science, engineering, and a lot of other fields of study. So, what I would like us to do is to be able to become adept at identifying when some of these notorious distributions might be applicable. So, based on a rough description of the process that you want to model, maybe given an average, maybe some measure of variation, can we propose a notorious distribution that might do the job for us? We know that all our probability models are going to be wrong anyway, so is one of these notorious distributions close enough to be a reasonable reflection of reality? So let's take a tour through the couple of notorious distributions that are applicable to counts. Now, the building block of a lot of notorious distributions is a distribution known as the Bernoulli distribution. Now, in a Bernoulli trial, we're essentially observing the outcome to a single trial of a random process. So a surfer clicks on an ad or they don't click on an ad when they see it. A customer either does churn or they don't churn after their contract has expired. So a Bernoulli distribution has exactly two outcomes. One we're going to call 1, the other one we're going to call 0, and we're going to associate 1 with a success, whatever event really interests us, and the 0 is going to be associated with a failure. Basically, our event didn't occur. The Bernoulli distribution takes the probability of observing a 1 as p and the probability of observing a 0 as 1 minus p. There's a nice equation that kind of sums that up that we can plug in 0 or 1 into to get those p and 1 minus p's out. But in essence, the Bernoulli distribution is the simplest of discrete distributions because it just has two possible outcomes, one with probability p and the other with probability 1 minus p. Now, more often in business analytics, we're interested in knowing, well, what happens over multiple trials? The Bernoulli distribution is great for letting us know what happens during one particular trial. Do we get a click or do we not get a click? But what if we wanted to answer the question, well, what's the probability that after 1,000 surfers have viewed this website, that at least 40 have clicked on the ad? So very often in business analytics, we're interested in answering the question, well, what's the probability of observing exactly k successes out of n trials? What's the probability of observing exactly 40 clicks after 1,000 surfers have viewed the ad? What's the probability that exactly 30 days out of the year had a stock out when the probability of a stock out in any particular day is maybe 3%? So whenever you're thinking about some process that you want to model and it boils down to counting up the number of times some event of interest occurred out of a fixed number of trials, well, your binomial distribution is going to be your go-to distribution. So what does its PMF look like? Well, the possible values of x are going to range anywhere from 0, 1, 2, 3, all the way up to little n. We'll reserve little n to be the number of trials under consideration. Little x is going to be the number of times our event of interest occurred, our number of successes. We're going to have a formula that kind of harkens back to our discussion about combinatorics, actually counting up something. We see a p raised to the x power. We see a 1 minus p raised to the n minus x power, where p is that probability of our event of interest occurring a success. So where does this formula come from? Well, we actually have the skills to be able to derive this from first principles. So let's actually do that. Let's see why this formula is the way it is. So let's look at this in terms of a real-world context. Let's imagine that on our way to work from home, we have to pass through 5 different stoplights. So let's assume the outcome of each stoplight is independent of one another, and we're either going to see a red or a green when we show up to it. So the outcome of each individual stoplight is a Bernoulli trial. We either see a red or a green, 2 outcomes here. We're interested in counting up maybe the total number of greens that we run into on our way to work. So whenever we're counting up the number of times something happened out of a fixed number of trials, binomial distribution, let's see how this formula arises. So let's try to figure out the probability that exactly 2 of these stoplights are going to be green. And we'll assume that each stoplight has a probability P of 20% of being green when we show up to it. All right, well, one way that we could observe exactly 2 greens is if the sequence of lights was green, green, red, red, red. Now, if each light is independent of one another, we know that when we are asking the question, what's the probability of some combination of independent events, we just get to straight up multiply together the component probabilities. So the probability of the sequence, green, green, red, 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 would be the probability of green times the probability of green times the probability of red times the probability of red times the probability of red. So working that out, we get 0.2 times 0.2 times 1 minus 0.2, the probability of red, multiplied by itself 3 times, or 0.2 raised to the second power, 1 minus 0.2 raised to the third power. Now, of course, that's not the only way that we could have achieved a sequence with exactly 2 greens. It could have gone green, red, red, or maybe red, green, red. But if we think about it, since the outcomes of the lights are independent of one another, every possible sequence, every possible reordering of those greens and reds are going to have the same probability. Green is going to appear twice, so we'll have a 0.2 squared times a 1 minus 0.2 raised to the third power to represent 3 reds distributed somewhere across that sequence. So we know that each sequence of 2 greens and 3 reds has this probability. How many possible sequences are there? Well, if we dust off our notes back when we talked about how we count, we talked about exactly this sort of question. If we had a sequence of 2 different types of objects, reds and greens in this case, the number of possible sequences is related to that choose function. If we have a sequence of length 5, and we're mixing together 2 greens and 3 reds, there's going to be a total of 5 choose 2 or 5 choose 3, they work out to be the same number, possible sequences here. So the formula for the binomial distribution is now fairly clear. So if each trial has a probability of success of P, and we're going to count up the total number of successes out of n trials, well, the probability of observing exactly little x successes is now clear with this formula. The p raised to the x power represents the probability of finding exactly x successes along that sequence. The 1 minus p raised to the n minus x power is the probability of observing the remaining values to be failures, not successes, distributed across somewhere along that sequence. How many total set sequences are there? They're all going to have the same probability. Well, n choose x. We have a sequence of length n. X of them need to be successes. The n minus x remaining need to be failures here. So we're actually able to derive that binomial distribution with absolutely no problem, and we know it as the go-to distribution whenever we're counting up the number of times that some event of interest happens out of a fixed number of trials. So what does the PMF actually look like? Well, let's head on over to the Shiny app for our Notorious zoo, and we'll head down to the binomial distribution. This allows us to tweak the 2 parameters of the distribution, the number of trials that we're considering, and also the probability of success for each one of these trials. So there are some options for having the bar start at 0 and ending at n, because we know that technically any value between 0 and n, including those 2 values, are possible. So I'm going to fix that to vary over the whole range of values, and we'll just see, well, what does this shape look like? So for a probability of, say, 0.76, as I vary the number of trials, I see that the shape stays roughly the same. It's roughly symmetric here. As I change the probability, well, that kind of just changes where that peak is along the possible values of x. And so I see overall that the shape of a binomial PMF is roughly symmetric, and I can actually tell you approximately where that peak in that distribution is going to be. That's the kind of the average value or the expected value. If we took the number of trials and multiplied it by the probability of success, that's going to be the approximate location of the peak. And that makes sense because if, say, 25% of trials should end up with a success, if we're dealing with 100 trials, well, we would expect just about 25. Looks like that matches up. So obviously, we're not going to type out that full equation in R if we want to work with the binomial distribution. R has a whole bunch of built-in functions that allow us to work with these notorious distributions with very little effort on our part. So the way that we're going to work with R is to identify essentially the abbreviation that R knows the probability distribution by. Binomial in this case is going to be binom. And what we're going to do is we're going to preface binom with a single letter, either D, P, Q, or R. If we preface it with D, D binom, that's going to give us the probability of observing a certain value of little x. So x successes out of n trials where the probability of success is p. If we preface that with a little p, that's going to let us know what the CDF is, capital F evaluated at x. So p binom is going to let us know the probability of observing at most x successes out of n trials where the probability of success is p. Prefacing it by a Q gives the quantiles of the distribution, more on that later. Prefacing it by an R gives us random numbers from the binomial distribution. So we can use D binom, P binom to answer questions very quickly. So what's the probability that exactly 3 out of 48 people in a classroom are left-handed if the probability of being left-handed is 10%? Well, since I'm asking about the probability of some number of successes, I'll preface binom with a D to get the value of the PMF itself. D binom, 3, 48, 0.1. The number of successes, number of trials, probability is going to get me that answer right at about 15%. What's the probability that at most 3 out of 100 people churn if each person independently has a 2% chance of churning? Well, at most 3 corresponds to the values 0, 1, 2, or 3. And so in this case, I can throw the vector 0, 3 at D binom to get the probabilities of each one of those 4 values, and then just take the sum of the result. So I can very quickly get the probability of getting at most 3. But of course, at most 3 is kind of the cue in our head that says, hey, I should really be dealing with the CDF here, the probability of observing at most a certain value. If I preface binom by P in this case, and throw 3 in there, that'll let me know the probability of observing at most 3 successes, at most 3 churns out of 100 people, where the probability of churning is 2%. Come up with the same answer either way, so you can choose your favorite. Now, what if we're dealing with a trial that has more than 2 outcomes? Bernoulli trial was success and failure. Binomial is counting up the number of successes as opposed to failures after n trials. What if for each trial we have multiple possible outcomes? So we show up at a stoplight, it might be red, yellow, or green. We open up a pack of M&Ms, we might get a red, a yellow, an orange, a green, a blue, or a brown. How would we describe the probabilities of particular combinations of outcomes after n trials? Well, the multinomial distribution is our generalization to the binomial when we have more than 2 outcomes to each trial. So, for example, let's imagine that we are handing out fun packs of M&Ms for Halloween to the trick-or-treaters. Hopefully there'll be some this year. And each of these fun packs has 24 M&Ms in it. So there's a probability distribution that describes the probability of each one's of the different colors. And so we might want to ask the question, well, what's the probability that I would have exactly 4 of each of these 6 colors? So because I'm asking for the probability of some combination of outcomes after 24 trials, I'm going to be able to use the multinomial distribution to help me answer this. So to do this, what I'm going to do is to define a vector x that tells me the number of each type of outcome in my question. In this case, it's just a vector of 4s because I'm interested in knowing the probability of seeing 4 for each one of those colors. And so I'm going to define a corresponding vector p that gives me the probability of observing each one of those particular outcomes on any given trial. So 20% chance of observing green, orange, blue. Let's have that be the first, second, and third elements of p, the first, second elements of x here, the number of greens, oranges, and blues that I get out of those 24 trials. 15% chance of yellow and red, and 10% chance of orange. If I throw that into the D multinomial function, x comma p, that lets me know the probability of that particular combination of outcomes, 4 of each color, after 24 trials. Now, D multinomial isn't a built-in function in R. You can find it in the corresponding .r file in these notes. I've kind of just written it here for you because the actual formula that gives us the probability of any particular combination of interest after we've conducted n trials is a bit unwieldy. If you go dust off your notes about combinatorics and figure out, okay, well, how many ways can we rearrange a sequence with exactly, say, 2 oranges, 3 greens, 5 blues, etc., you find that this kind of massive hulking combination of factorials appears in there. This is the number of ways you can rearrange a sequence where the first outcome appears n1 times, the second outcome appears n2 times, etc., etc., where the probability of observing outcome 1 is p1. So a lot of math that goes in there. We can get it by hand, but this nice custom code will help get us there very quickly. So if we're still basically counting up the number of times something happens, but we're counting up multiple outcomes at once, that generalization of the binomial distribution, this multinomial distribution, is going to be our go-to. Now, another notorious distribution also builds off the idea of Bernoulli trials, but in this case, we're counting up the number of Bernoulli trials that result in failure before the first Bernoulli trial that results in a success. So we kind of talked about this with the telemarketer example. The telemarketer is calling up a customer again and again and again and again, and we were interested in knowing, well, when is that telemarketer finally going to make a sale? This notorious distribution, the geometric distribution, would actually be our go-to in this case. The geometric distribution counts up the number of failures in a sequence of Bernoulli trial before that very first success. So we have a formula that actually gives us the PMF, and it's easy to derive. We can actually just do it in our head. For that very first success to happen after X failures all in a row, well, the probability of a failure is 1 minus p if all the trials are independent. 1 minus p multiplied by itself x times will give us that sequence of x failures all in a row, then followed by a single success at the end with probability p multiplied together. We get our expression out. The possible values of x are 0, 1, 2, 3, 4, 5, technically going up to infinity. A value of x equal to 0 means that success on the very first trial, 0 failures before that first success. All right, so what does the geometric distribution look like? What do we actually use it for? Well, the geometric distribution is always going to be used when we're looking at waiting times. So how many failures do we have to experience before that very first success? Here we have our geometric PMF here with a slider that lets us know, all right, well, what's the probability of success? The heights of those bars lets us know the probabilities of observing a certain number of failures before that very first success occurs. So regardless of what the value of p is, this actually has the same shape. It just decays rather quickly. It gets smaller and smaller and smaller as we go up to larger and larger values of x. And the peak, the highest bar, is going to be 0 regardless of the value of p here. And that makes sense. In order to have, say, an x equal to 1, 2 things have to happen. I have to have 1 failure followed by 1 success. If I had an x equal to 0, only 1 thing has to happen, essentially success on that very first trial. So because larger values of x correspond to basically more complex events happening, whenever a combination of events are occurring, I'm multiplying together probabilities, they're all between 0 and 1, that product is going to get progressively smaller and smaller and smaller. So the highest bar for a geometric, always at x is equal to 0. We're going to go to this geometric distribution whenever we're dealing with some random quantity that is related to the number of failures before our very first success. The number of trials something doesn't happen until it finally does. So where might I use this? Well, you know me, I love my gems. I love playing that bonus game. It's amazing. Feels great. You win a lot of money. I might like to know if any particular game has a 4% chance of yielding that bonus game. All right, well, what's the probability that I'll have to play, say, at most 50 games before I get to play the bonus game? So what's the probability of at most 50 failures before that first success? That would be asking the question, what's the probability that a geometric distribution has a value that's less than or equal to 50, where p is equal to 0.04, the probability of success on any particular trial. It's actually very useful to use the geometric distribution when studying customer churn. Maybe a customer churns after their first bad experience at a store. So they show up, have a great experience, they end up coming back. They show up, they have another great experience, they end up coming back. They show up, terrible experience, they never show up again. So we can imagine that maybe the probability of having a bad experience, which we'll call a success, that's really our event of interest, kind of a weird way to think about it, but that's what we'll do. If the probability of having a bad experience is 10%, we might like to know, well, what's the probability that the total number of visits is at most 8 before this customer churns? So what's the probability of at most 8 failures, basically 8 good experiences, before that very first bad visit, where the customer doesn't return? Well, that would be the probability of observing a capital X, our value for our random variable, less than or equal to 8 here. Now, one really cool quirk or unusual quirk about the geometric distribution is that it is memoryless. Now, what does that mean? Well, if we think in terms of using the geometric distribution to model waiting times, basically the number of trials for something to first occur, essentially what this memoryless property is letting us know is that it doesn't matter how many failures we've waited already. The expected number of trials until our very first success is going to remain the same. So if we're interested in picking an orange candy out of a bag of M&Ms, it doesn't matter how many non-oranges we've picked out so far. The probability that our first orange candy is going to happen in the next 5 is going to be the same, even if we've picked out 10 non-oranges beforehand, 50 non-oranges, etc., etc. And this kind of flies in the face of our intuition. We expect that, after a whole long string of failures that we're kind of due for a success. But if all of the trials are independent, the geometric distribution is doing a good job at modeling the number of failures before that first success, it turns out that the number of failures that we've experienced so far doesn't influence the expected number of trials until that very first success. So how does this work? Well, let's give it a little bit of a real-world context. We want to get this orange M&M out of this bag. 20% of M&Ms are orange, so we open up a fresh bag. We're excited to get that orange M&M, so we start picking out those M&Ms one by one. So we pull out 10 candies, and much to our dismay, none of those candies turn out to be orange. So surely that's got to be luck. On average, 1 out of 5 of these candies should be orange. So surely we're due, after 10 failures, to have this next orange candy coming up right away. Well, it turns out that no, there's no such thing as being due when we're treating the colors of M&Ms on sequential candies as independent. It turns out that the waiting time, the number of additional candies we have to dry out from that bag until we get that first orange, is independent of the number of non-orange candies we've pulled out so far. So it doesn't matter if we just open that fresh bag, if we picked out 50 non-orange M&Ms, if we picked out 100, the answer is going to be the same regardless. So how can the math convince us of that? Intuition probably says that doesn't seem quite right. We're kind of due for this event to occur. Intuition and probability rarely go hand in hand here. So let's examine why that's the case. All right, so let's first start out by figuring out what is the probability that we would get an orange candy at some point during the course of pulling those first 5 candies out of the bag. Or in other words, what's the probability that we get at least 1 orange candy out of the first 5 we pick? Well, whenever we hear, the probability of at least 1, that should immediately ring some bells and say, hey, let's actually calculate the complement of that event. That's usually easier. Let's go down that route. So the complement of at least 1 orange out of the first 5 is exactly 0 oranges out of the first 5. And that's easy to calculate. If the color of the M&Ms is independent from one candy to the next, and the probability of getting an orange is p, the probability of not getting an orange on any particular candy is 1 minus p. To have it 5 times in a row, we would have 1 minus p raised to the 5th power. And so the complement of that event, the probability of getting at least 1 orange candy out of the first 5, will be that 1 minus p raised to the 5th power. It works out to be right at about 67%. All right, so fresh bag, there's about a 2/3 chance that within those first 5 candies, we'll pick out an orange candy. So let's start to do some conditioning. Let's start to look at what happens if we've picked out 10 non-orange candies, 50 non-orange candies, or in general, let's say we've picked out n non-orange candies. Well, now what's the probability that we're going to pick out an orange at some point during the next 5 candies we select out of that bag? So let's review our formula for calculating conditional probabilities. The probability of A given B is the probability that both occur, divided by the probability of the event on which we're conditioning. So in this case, event A is the event that we get at least one orange candy out of the next 5 we draw out of the bag, and event B is the event that the first n candies that we've drawn out of the bag are not orange. So using our formula for conditional probability, that works out to be the probability of succeeding in the next 5 trials, and the first n trials were failures, divided by the probability the first n trials were failures. Well, the denominator is pretty easy to calculate since each trial is independent of one another. The probability of a failure, a non-orange M&M, is 1 minus p. That would just be 1 minus p raised to the n power. And so now let's do the numerator. Well, the probability that we would get at least one success in the next 5 trials and the first n trials were all failures, since, once again, this is a combination of independent events. The color from one M&M to the next is independent. That would just be the probability of that sequence, failure, 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 n failures in a row, followed by at least one success out of the next 5. Well, we know the probability of having n failures in a row is 1 minus p raised to the n. We just calculated that in the denominator. And then the probability of getting at least one success at some point in the next 5 trials, that's our 1 minus p raised to the 5th power that we had just calculated, assuming we had opened up a fresh bag of M&Ms here. So putting all those components into this equation, what we find is we have some glorious cancellation of these 1 minus p raised to the n power that appears in the numerator and in the denominator. So what we have left over is 1 minus p raised to the 5th power. So here's what we've discovered. If we condition on the fact that the first n trials were all failures, the probability that we get our first success at some point in the next 5 trials is actually the same number regardless of what n is, the number of failures before. We're kind of asking this question. So n could be 10, n can be 100, n can be 1,000,000. This process, for all intents and purposes, looks like it's kind of resetting itself. The probability of having that first success occur in the next 5 trials is the same regardless of how many failures that we've experienced so far. That's what we mean by this memoryless process, or memoryless property of the geometric distribution. And it turns out this is the only discrete distribution that has this property. Every single other discrete distribution out there would have this probability change as we accumulate more and more failures. So kind of a cool little quirk. A related distribution to the geometric is the negative binomial. Now, I'm not a fan of the name of this distribution because it doesn't directly tie into the binomial distribution. The formula kind of looks the same, but it's really quite different. It's more of a generalization of the geometric distribution. Instead of counting up the number of failures until that very first success, it's counting up the number of failures until success number r. So to put this in a bit of context, let's imagine that you're hired to hand out flyers to random people on the street. You're given, say, 100 flyers to distribute. So when you offer a flyer to somebody, they may accept it, they may not accept it. Essentially what you'd like to know is, how many people am I going to have to offer flyers to until I'm done for the day? So if we consider, say, a success as someone actually accepting one of these flyers, we'd be interested in counting up, say, the number of failures, the number of people who don't accept that flyer, until we achieve that 100th success here. So how could we develop the formula for the PMF? Well, it's actually not so difficult to conceptualize. So in order to have the rth success happen on the very last trial, and to have x failures before that occur, well, the sequence must be some mixture of x failures and r minus 1 successes, followed finally by a success on that very last trial, that rth success on that very last trial. Okay, well, in order for that sequence to occur, well, we need to have r successes in total. Each one has a probability p. We need to have x failures in total, with probability 1 minus p. So p to the r times 1 minus p raised to the x power gives us the probability of any sequence where we have some mix of x failures, r minus 1 successes, followed by the very, very, very last outcome being a success. The question becomes, okay, if all of those trials have the same probability, how many of those sequences exist? How many ways can we rearrange X failures and R minus 1 successes? Well, we know how to count that. The total length of that sequence would be X plus R minus 1. That's what we're rearranging, X failures, R minus 1 successes. And what we're doing is we're rearranging it so that each sequence has those X failures and R minus 1 successes. So X plus R minus 1, choose X gives us the number of sequences where we mix together the ordering of the X failures and the R minus 1 successes. So done. The possible values of X are 0, 1, 2, 3, etc. X equal to 0 would mean, every single trial resulted in a success. The first R trials were all successful. And so we can see that this negative binomial distribution is very much a generalization of this geometric. If we're interested in the number of failures before success number R, boom, negative binomial is who we're going to run to. Now, going and looking at what this negative binomial distribution looks like on the Shiny app, what kind of shapes can it provide to us? Well, let's take a look. So once again, there's going to be two parameters here. P is going to be the probability of success on any particular trial, and we're going to have the R parameter, basically the target number of successes. And the possible values here, it's being labeled, this is the number of failures before we observe that 10th success. So what can we say about the shape of the negative binomial distribution? Well, if I'm fixing the probability at 53% here, what I find is that it can go anywhere from being fairly skewed off towards the right-handed tail here, kind of a slow decay toward larger and larger values, to being roughly symmetric if this value of R is relatively large. If I were to change this probability, well, what's my impression of the shape look like? And we can see, as we decrease the target number of successes, this distribution gets more and more skewed. As we increase that target number of successes R, it becomes a bit more and more symmetric. So this negative binomial, and this will be important in a second here, actually has a pretty wide variety of shapes. Most of them are slightly skewed towards the right, towards larger values, but depending on the particular combination of parameters, we can get rough symmetry if we get those parameters right. So that's what the negative binomial distribution looks like. And once again, where do we actually use it? We use it whenever we're asking something about the number of failures that have to occur before success number R. So how many people do we have to ask that say, no, I'm not interested, until we pass out those 100 flyers, have those 100 successes? And actually tying this back into churn management, the negative binomial would really be quite useful. So let's imagine that a customer churns when they have their third bad experience. So if we consider a success as a bad experience, this is basically what we're interested in asking. So when is that third success going to happen? When is that third bad experience going to happen that causes them to churn? So we might imagine that on a particular visit to a store, the customer might have a bad experience, a success in this case, with 10%. We might be interested in asking questions like, well, what's the probability that the total number of visits or total number of good experiences is at most 8 before they end up churning? A good experience in this case would be considered a failure with our terminology, kind of weird, but we'd be counting up the number of failures until that third success, that third bad experience that counts into churn. And so most questions actually, when we're really asking this question in business analytics, isn't necessarily about the total number of failures before a target number of successes. It's about the total number of trials that occur in order to get that Rth success. But there's a really easy way to translate between these two questions, the total number of failures and the total number of trials overall. So here's what we're going to do. If our question really is about the trial on which that Rth success occurs, what we're going to do is we're going to use a very particular value for little x, the number of failures. Specifically, we're going to use a value of little x to be capital N minus R, the trial on which that Rth success occurs, subtracting off those R successes. If we use that as little x, that gives us the number of failures that we need to plug in to that negative binomial equation in order to get that probability. So, quick example just to see why this equation makes sense. If we want to know, all right, how long is it going to take for that fourth success to occur? R is equal to occur. And we really want to know something about the total number of trials. Let's say, what's the probability that it occurs on the 9th trial, that 4th success occurs on that 9th trial? Well, what is our sequence going to have to look like? So it's going to have to end with a success on that very 9th trial. We're going to have some mixture of successes and failures, 3 successes, and looks like a total of 5 failures for that 4th success to occur on trial number 9. We can see, asking the question, what's the probability that the 4th success occurs on trial number 9, is the same thing as asking, well, what's the probability of having exactly 5 failures before that 4th success? So little x equals to 5 would translate into a capital N, a trial number of 9 for the total number of trials if we had the question we wanted to ask it that way. All right, I think one of the most useful distributions in all of business analytics, and actually in all of science, is the Poisson distribution. And our Poisson distribution is going to be our go-to model when we're just counting up just something in general. So if it's kind of a count without a context, like we're not counting up the number of times something happens out of n trials, we're not counting up the number of failures until something happens, we just have some sort of generic count, the Poisson model is going to be our go-to distribution. So if we want to come up with a probability model for, let's say, the number of books that someone has checked out of a library, well, that's not really out of a certain number. It's not counting up the number of failures to a success. This is just a generic count, a count without a context. The Poisson distribution might actually help us out. Or if we're going to look to see, okay, we freeze time, we go look at people's shopping carts around Kroger, what's a probability distribution for the number of items they have in their cart? It could be 0, could be 1, 2, 3, 4, etc. There's no hard cap upper bound. We're not counting up the number of successes out of n trials. We're not counting up the number of failures before something happens. We just got a generic count in mind. The Poisson distribution, in this case, is going to be our go-to. So counts without a context, just generic counts. The Poisson distribution has proven to be immensely useful for coming up with a reasonable probability model. Now, the derivation of the formula for the PMF, the Poisson, is a bit from where we want to be right now in class. So I'm just going to throw it at you and just say, this is what it is. If I want to know the probability that the count will exactly equal to little x, it's going to be equal to the following formula. So the Poisson distribution has a parameter called lambda. It's the average value of the distribution, actually. We take lambda raised to the x power, multiply it by e raised to the minus lambda power, and divide by x factorial. So on average, we expect lambda, give or take about square root of lambda or so. That's the standard deviation. But that's how we can get the Poisson probabilities out. So what does that Poisson distribution look like? Well, heading over to our Shiny app, we only have one parameter for the Poisson. And as I vary that value of lambda to get bigger and bigger, what we find is that the typical values that we're seeing also get bigger and bigger and bigger. So going down from a small lambda, small values of x, big lambda, relatively big values of x. What we see is that for smaller values of x, we have a distribution that's skewed a little bit to the right. As we go up to larger and larger values of x, that distribution becomes more and more symmetric, but still with a little bit of a right-handed skew here. So those are the shapes that the Poisson distribution can get for us. How can we use this distribution in R? Well, R knows the Poisson distribution by pois, P-O-I-S. So dpois would give us the values from the PMF, the probability of observing a value exactly equal to 3, exactly equal to 5. Ppois would give us the probability of observing a value of at most 10, or at most 5 here, so 5 or less. Rpois would give us random numbers from a Poisson distribution. Now, in business analytics, a slight modification to the Poisson distribution might prove actually more useful than the Poisson distribution itself, because a lot of things that we count in business analytics don't actually have 0 as a valid quantity. So for instance, if we were counting up, let's say the number of items that someone has in their shopping cart at checkout, well, there are not going to be any shopping carts with no items in it when someone pulls up to the checkout here. 1 is the minimum possible number. So when that's the case, when we're basically trying to model some generic count, some count without a context like an out of or until, but 0 is not a possible value, we're going to use the zero truncated Poisson instead. We're going to abbreviate that by a ZTP, and we're just going to take our definition of the Poisson distribution and modify it so that 0 is not a possible value. How can we do that? Well, we can do some conditional probability. So what is the probability that our count is going to be equal to little x, given that we know that the count is bigger than 0? Well, the probability of A given B is the probability of both divided by the probability of the event that we're conditioning on. So we can rewrite that probability as the probability of observing exactly little x and x being bigger than 0 divided by the probability that the number of items would be bigger than 0 here. And if we think about it, those two conditions in the numerator are redundant. We're already placing the condition that little x is bigger than 0, so asking what's the probability that big X is equal to little x and big X is equal to 0, that's redundant. We already know that big X is bigger than 0, so that numerator just becomes the probability that big X equals to little x with that Poisson distribution. And the probability in the denominator, the probability that x is bigger than 0, easier to do the complement, 1 minus the probability that x is equal to 0 here. So taking our formula for the PMF of the Poisson and plugging in those relevant quantities, we find that the PMF for the zero truncated Poisson is as follows. Kind of a complex formula. R doesn't have a built-in function for this one. We can write it on our own or actually load up some other packages that do have the zero truncated version. But we can easily get it just by referring to dpois. If we want to know the probability under a zero truncated Poisson model of having exactly 4 items in the cart, well, we can dpois 4 divide by 1 minus the relevant value of lambda. All right, so that Poisson distribution is really our go-to model for counts in business analytics and really just science in general. But what people have discovered is that very often the Poisson distribution doesn't quite cut it. It turns out that for real-world data, very often the variation in values, the range of values that we see, is a little bit bigger than what the Poisson distribution can really give us. So when the Poisson distribution proves to not be that great of a fit, what we end up doing is actually turning to the negative binomial distribution as a backup. And we'll discuss exactly what the relationship is between a Poisson distribution and a negative binomial distribution at a later time. But for right now, what I want you to know is that the negative binomial distribution isn't just restricted to cases where we're counting up the number of failures before success number R. It's actually a really good alternative to the Poisson distribution when the actual variation in values that we've collected are a little bit bigger than what the Poisson distribution can actually give to us. All right, last of the notorious distributions, this is pretty much the last resort for a probability model when we don't really have much information about the process. So the uniform distribution just says that every single integer within a range is equally likely. So if I wanted to know, well, what's a good PMF probability distribution that lets me know what the value is on the minute hand is on a clock when I show up in a room at a random time, well, all values between 0 and 59 would be equally likely, so there would be a case that you have a good use for the uniform distribution. Sometimes you just don't know much about the business process. You might just know, well, I know the values I'm going to get range somewhere between 10 and 15. I couldn't tell you which one's more likely, so you might just impose a uniform distribution over those possible values. So not a very interesting distribution to work with, kind of our last resort. Here's a visualization for it. If we increase the range of values we might have seen, of course, the probability of observing each one of those in particular values gets smaller and smaller as we include more and more, because that probability is just getting spread out over more and more values here. All right, so quick refresher about how to use these notorious distributions in R. So if you want to use the binomial, you want to use the Poisson, you want to use negative binomial, you want to use the geometric, first you need to identify, okay, well, what is the name by which R knows this distribution? So R knows the binomial distribution as binom, the Poisson distribution as ppois, pois, the geometric distribution as geom, geom, and negative binomial, n, binom. So once you know what that word is that R knows the distribution by, What you're going to do is you're going to preface that word with either a D, a P, a Q, or an R. The D is for values from the PMF, so the probability of observing a particular value. P is for the CDF, capital F, the probability of observing at most a particular value. Q is for quantiles, more on that later, and R is for generating random numbers from that distribution. Very useful for Monte Carlo simulation. So something like our binom would take as its first argument n the number of random values you want from this distribution. Then you would follow it up by, okay, well, what is the total number of trials, your size parameter, say 20, and probability of success, 0.5. What is the probability that at least one of those candies out of the first 5? Let's start again. Stop. Nope, flyers is a much better way to go about doing it. Flyers are a much better way to go about doing it. You should start with that. It's a lot more fun. They'll know what you're talking about.